Okay, good morning, everyone. I hope you're all well. Before we jump back to the business of today, just some good news I wanted to share with you. I mentioned we're going to talk about computer-designed organisms and xenobots at the end of the course this year. The lead author on the work on xenobots was Sam Kriegman, who's now my PhD student, but he took this course a few years ago. And we just found out yesterday that Sam's paper on xenobots won one of the six 2020 Cozzarelli Prizes. The Cozzarelli Prizes are given out each year by the National Academy of Sciences. The NAS is the leading body for scientific research in the United States. They give out one award in various categories: physical and mathematical sciences, biological sciences, and we were extremely happy to hear yesterday that our work on creating evolutionary algorithms that automatically design robots made out of biological cells won one of the six Cozzarelli Prizes. So good news for the xenobots, good news for Sam, a former student in this course. Okay, speaking of this course, where are we and where are we going? We are working our way through our history of evolutionary robotics. You are now starting in on assignment 7. Assignment 7 has a part A and a part B. 7A is going to be implementing synapses. And just to sort of show you where this fits in, obviously your code base now is growing relatively large and somewhat complex. So I've sprinkled these figures throughout the assignments to try and to remind you of the big picture of what you're constructing. Towards the beginning of the semester, you created an empty simulation in PyBullet. You then created a generate file, which initially generated a world using the help of Pyrosim, which outputs an SDF file. That world is made up of a series of objects known as links, and PyBullet calls bullet, and bullet applies forces to the links, which updates their positions and orientations. Then you added the body of your robot, which is stored in a universal robot description format file, or a URDF file. A robot is also made up of links, but those links can be connected together with joints. Joints apply forces to the links that they connect, which again updates the positions and orientations of the links that make up the robot. Later on, you added in sensors. You then added in motors. Motors apply forces that are passed on by the joints to the links. In the last couple of assignments, you've been working on adding a brain to your robot, generating the brain as well. The brain is made up of a number of sensors and motor neurons. Motor neurons output numbers. Those numbers are interpreted by the motors as desired angles. The motors figure out how much torques or rotational force to add to joints to try and reach those desired angles. The values arriving at the sensors are input into the sensor neurons. So in assignment 7A this week, you are going to be closing the loop, the sense, think, act loop that occurs in every robot by connecting your sensor neurons directly to motor neurons with synapses. In a lot of the neural networks we've talked about so far, sensor neurons are connected to hidden neurons by synapses, and then hidden neurons are connected to motor neurons with synapses. We're just keeping things simple for the moment. We have synapses connecting directly from sensors to neurons. So far, so good? Okay. The second part of the assignment this week is 7B, where you're going to be creating the first in a series of increasingly powerful search engines. And we're going to start with the search methods. We're going to start with the simplest possible search method you can think of, which is random search. So I've renamed the generate file to search.py here. You're going to be searching over a set of solutions. What is a solution? A solution at the moment is just going to be the weights of the synapses that connect the sensor neurons to the motor neurons. Change the weights of these synapses, and you change the flow you change the way this sense, think, act, closed loop controller works. Okay, that's where we're heading. Any questions about assignment 7, the previous assignments? All good? Okay, so let's carry on. Last week, we were working our way through a series of 4 experiments, which were the initial minimal cognition experiments. This was an attempt to try and keep the agent as simple as possible and see how or whether we could evolve the various building blocks of intelligence. I realized by looking over the lecture notes from last week that I actually missed a few slides from lecture 8 when we talked about C-tier and Ns. So I'm going to back up for a moment. We're going to finish lecture 8. And then we'll jump forward again to lecture 9, and I think we'll have time to start in on lecture 10 today. Okay, so a little jumping around today. Back to lecture 8. And in lecture 8, just to refresh your memory, we worked our way up by building up our understanding of what a C-tier and N is. If we have N neurons in a C-tier and N, we have N ordinary differential equations, which describe how the ith neuron, or how each neuron in the C-tier and N changes over time. We introduced a bunch of parameters, tau, weights, gains, and offsets. And evolution can play with all 4 sets of these parameters to alter how these neurons influence one another, which influences how they continuously change over time. Okay, what I forgot to talk about when we talked about lecture 8 was an application of C-tier and Ns. This is a bit of a more advanced and involved experiment than the ones we've seen so far. So this discussion in the next few minutes is mostly directed at the graduate students. If not all of you follow along, that's perfectly fine. There's a link to the paper here. You can dive down into the details. There's a lot of details. I'm going to just try and summarize the main findings of this experiment today. Okay, as you can see, we have a little humanoid robot here, and I think I have a video of it. Here it is. You'll notice that this little humanoid has a block in front of it, and this robot, we are going to teach this robot to do various things. Let me see if I can skip ahead a little bit here. You can see that part of what it's learning is through human instruction. The human is literally, the human is helping the robot move through what it's supposed to be doing. For our purposes at the moment, it's just important to realize that this robot is evolving the ability to, for example, lift up the block up and down a couple of times. That's not the only thing it's asked to do. It also evolves the ability to move the block left and right a couple of times. So nothing too complicated. However, getting a robot to learn to pick up a block and lift it up and down 3 times, that's not too difficult. But learning, teaching the robot or training or evolving the robot to lift the block up and down 3 times, and then left and right 3 times, and then forward and back 3 times, and then up and down 3 times is more difficult. This is known as teaching motor primitives. As Luke says, it's so cute. Absolutely it is. And this is another important building block of intelligence that we haven't talked about so far. You can do lots of things. You can run and jump and ride a bicycle and ride an airplane and ride a subway. Each of those abilities that you learned is made up of a series of motor primitives underneath. So if we take walking, for example, walking is made up of a number of simpler actions like extending your leg. You can think about performing a triathlon, which is, well, let me see if I can remember how this works. Swimming, biking, and then running. So there you have an activity, doing a triathlon, which is made up of 3 motor primitives, swimming, biking, and then running. And each of those activities, like walking or running, is made up of a series of simpler motor primitives like extending your leg and knowing how to flex your leg and pull your leg backward. So there is in intelligence the idea of a motor hierarchy, being able to build more complex abilities by stacking or hierarchically arranging simpler abilities or motor primitives. So in this study, they're going to evolve a CTRNN, which I've rewritten for you over here. They're going to evolve a CTRNN to get this robot to learn motor primitives and then learn how to stack them together. So here's our little robot here. It always starts in the home position with its hands up here. We then tell the robot, it receives a teaching signal. So we inject a number from outside, and that number, when the robot receives that number, it should, for example, move up and down 3 times. If it receives a different number, it should move the block forward and backwards 3 times. If it receives a third number, it should know to move left and right. So we can basically tell the robot what to do by injecting different numbers into the CTRNN, and it should do the right thing. If we input a sequence of numbers, then it should do a sequence of actions like start in the home position, reach for the object, move the block up and down, clap its hands 3 times. Let's go this way. Home position, clap hands 3 times, and then back to the home position, or home position, clap 3 times. And although there's not an arrow here, move left and right 3 times, clap 3 times again, move left and right 3 times, then back to the home position. We should be able to tell it not just what we want it to do, but tell it to do a sequence of things. How do we get a robot to learn a hierarchy of different motor primitives? Well, we could break this CTRNN up into 3 small modules. What do I mean by modules? Remember, we have a whole bunch of neurons. We could take a subset of neurons and wire them up, take a second subset of neurons and wire those up, take a third subset of neurons and wire those up, and have no synaptic connections between these 3 groups. That's what these 3 modules are meant to represent down here. We could then evolve the parameters of these CTRNNs so that when we tell the robot to, for example, lift the block up and down 3 times, let's assume that's the green here. When we evolve the robot to pick the object up and down 3 times, we're evolving these weights, and if these neurons are allowed to control the motor neurons, the robot will indeed lift the object up and down 3 times. So you can see that this module has a gate, which means we could sort of turn or allow this set of neurons to control the motor neurons, and we could evolve these parameters to produce up and down motion of the block. We could then, in the same CTRNN, send in the second signal for moving the block left and right, allow these neurons to control the motor neurons, and evolve the parameters of these neurons to produce left and right motion when we ask for it. And the same thing for the third module. So if there are n different things that we want the robot to do, 1, 2, 3, 4, 5, 6, 7, 8 different things we want the robot to do, maybe we would have 8 subsets of connected neurons inside this neural network, and evolve each of them when they control the motor neurons to do what they're supposed to do, and evolve synaptic weights in here that allow signals to come from one module to the motor neurons at different times. We could do this, but it's got an obvious disadvantage. It has several disadvantages. What are they? While you're thinking about that, and if you have an idea, go ahead and type it into chat. Does your brain work this way? You can do thousands, arguably tens of thousands of things. Do you have 10,000 little modules in your brain? One for walking, one for riding a bicycle, one for riding road bikes, one for riding, one for skiing, one for snowboarding, one for writing. What's the disadvantage of that approach to learning an increasing number of motor primitives. Any ideas? Alex says the modules don't transfer to new or slightly different environments. Exactly. So maybe you train yourself to ride a bicycle. If you then train yourself to ride a Peloton, I guess maybe riding a Peloton is not that difficult. It's kind of like riding a bike, but kind of not like riding a bike. Do you need to start from scratch? Do you clone the module that allows you to ride a bicycle and modify that neural module to allow you to ride a Peloton efficiently? Logan says it would use up a lot of memory and space and become expensive. So Logan's hit the nail on the head. The main disadvantage of this approach is it's non-scalable. It might work if we want this robot to do 3 things, but if we want it to do 10 things or 100 things or 1,000 things, maybe we start to have a CTRNN that has tens upon tens of thousands of neurons. It's not very scalable. So in this paper, what they're going to do as they're training this robot to perform different motor primitives is to use a different approach. They're going to break the CTRNN into 2 different groups. I think I have a better picture of this further along here. Actually, 3 different groups. The first group over here, this is a mixture of sensor and motor neurons. Normally, we've seen this with sensor neurons on one side and motor neurons on the other. Here, they're just mixing them up. Then there are these 2 groups, which we're going to focus on today. These 2 groups of neurons, the ones in here are fast neurons, or fast units, as they call them here. And this group of neurons are going to be slow neurons, or slow units. There's going to be dense connectivity. There's a lot of synaptic connections among the fast neurons, and a lot of synaptic connections between the slow neurons, and a few synaptic connections between the fast and slow neurons. And then as I just showed you in the other slide, the fast ones connect to the sensor motor neurons. Let me skip ahead so you can see that. Here's the fast neurons, here's the slow neurons. The fast ones connect to the sensor motor neurons, which control the robot. What do I mean, or what do the authors mean by fast units and slow units? What did they alter in the CTRNN to make that happen? Which of the sets of parameters up here did they have to alter, did they tweak to make some of the neurons act quickly or respond quickly, and others to respond more slowly? You'll have to cast your mind back to lecture 8 and our discussion of CTRNNs. Anybody remember? We talked about Woody Allen neurons and Eeyore neurons. These are the Woody Allen neurons, these are the Eeyore neurons. Logan says it could be the strength of the connections. So actually by altering the synaptic weights, you can somewhat change the rate of response of units. It's not theta. So the investigators are going to set by hand some of these parameters to just make the neurons fast and make others slow, and they're going to let evolution alter the remaining parameters. Which ones did they set to make these neurons the Woody Allen neurons and these neurons the Eeyore neurons? Here's the equation for the ith neuron in the CTRNN. Logan just mentioned the weights, the W's over here. He also mentioned the bias over here. It's not either of those. No? Remember the taus over here. Let me just back up for a moment. Exact. George says the taus, right? So remember, we put the taus over here, and mentally in your head, we're just putting it on the left because it's easier to write this all out instead of writing it as a ratio. But if you divide both sides by tau sub I, you get y prime I equals minus y sub I divided by tau sub I. By altering tau, if we bring tau down near to 0, we have a denominator over here near 0, which means the rate of change of this neuron is always going to be of high magnitude. Could be negative, could be positive, but the rate of change is always going to be large. If tau sub I is a very large number, like near 1,000,000, then the right-hand side of this equation is minus y sub I divided by 1,000,000. So whatever is happening on the right-hand side of this equation, let's fill in the rest of the details here. We take this whole thing and we divide by 1,000,000. Whatever these values are, the rate of change is always equal to something divided by 1,000,000. The rate of change is slow. Okay, so why did they make so they're setting the taus in here to be very close to 0, and they're setting the taus in here to be large values, which means we now have a set of fast and slow neurons. And then they're going to evolve the weights and the gains and the biases to produce the behaviors they want. When we input a number saying lift the block up and down 3 times, or we input a number saying move the block left and right 3 times. Why did they do this? The idea here is to think of this like an orchestra. So you've got all the musicians here, but you also have the conductor who is slowly telling the musicians what to do. The purple curve here is meant to represent the change in activation of one of the slow neurons, the purple neuron. As this neuron is slowly changing, it is slowly altering the song that the fast units are singing or playing, if we continue the symphony metaphor. The conductor slowly changes what she is doing. That changes what the orchestra is doing. We can imagine that middle activation here of the purple curve, maybe this corresponds to telling the fast units to cause the robot to lift the block up and down 3 times. The conductor alters what she's doing slowly so that now she has a high activation, and that alters what the fast neurons are doing, and that might correspond to the robot moving the block left and right 3 times while she is holding her baton still at high activation. She drops her baton to a low value, and that pushes the orchestra into the 3rd blue motor primitive, which is pushing the block forward and back 3 times. Okay, it's a little bit more complicated. Conceptually more complicated than this. What's the advantage of this approach? Hopefully the advantage is a little bit more obvious, seeing as we focused on the main disadvantage of this approach. This approach is a little bit more scalable. If we want to evolve the robot to do 4 different things, we retrain the conductor and we train the symphony. And the conductor now raises her baton to a different level, a 4th new level, and that pushes the orchestra into this 4th song that they've learned, which corresponds to, for example, rotating the cube 3 times clockwise. We had a 5th task. We retrain the conductor and the musicians and that causes, this 5th song causes the robot to rotate the block clockwise 3 times. We're not adding any new neurons, we're just training the slow neurons to do something differently, and that should cause the fast neurons to do something differently, which should cause the robot to do the new task appropriately. Okay. So again, there's just a little bit more details. They set the taus for the fast neurons to 5, and they set the slow neurons to 70. They don't explain where they got these particular numbers. but that's fast and slow. Here's the single number, the goal, or what's known often as the teaching signal is coming from. It's a floating point number. And whenever this neuron receives a particular floating point number, it should cause the robot to do the task associated with that number. So far, so good? Any questions? Okay, let's look inside the brain of a robot that has been evolved to do the following. We're going to walk along the horizontal top of this panel for a moment. This robot was evolved to do the following: to reach. It was evolved to be able to lift the block up and down 3 times. It was also evolved, when it received an appropriate signal, to move left and right 3 times. And when it received, one signal, it evolved the ability to start here and reach for the object. When it received a different signal, it evolved the ability to lift the block up and down 3 times. When it received a different signal, it evolved the ability to move the block left and right 3 times. And when it received a fourth signal, it evolved the ability to go back to the home position. Okay. They then took that evolved robot and they input the first goal signal, then the second goal signal, then the third goal signal, and then the fourth goal signal, and lo and behold, the robot reached up and down 3 times, left and righted 3 times, and then went home. Okay, so I don't have a video of that robot. It might be in the YouTube video we just saw, but better to look at a figure here. So we have time on the horizontal axis here. And what is being plotted here is a bunch of the proprioceptive sensors. We've talked a fair bit about touch sensors so far, infrared sensors or proximity sensors. Proprioceptive sensors report the angle of the joint in the robot. You have proprioceptive sensors in your sensory cells in your muscles as well that tell you something about what is the orientation of your limbs relative to your main body. So proprioception in general gives you a sense of what is the state of your body. That's what we're seeing here. We're not going to talk about the teach signal for a moment. I'm sorry. I misspoke. The teacher signal, this is how the robot was actually evolved. We're not going to talk so much about, we're going to skip over that. Here's the robot proprioception. So this is the actual, the proprioception. These are the actual values of the proprioceptive sensors. And you can see these proprioceptive sensors telling us that the robot's arms were oscillating 3 times, and then the robot's arms were oscillating 3 times in a different way. This doesn't strictly tell us whether this was the correct up and down and whether this was the correct left and right, but you'll have to trust me that is the case. The robot was also looking at its hands as it was doing this, and you can see the visual sensors kind of reporting the same thing. Okay. We're now going to look at the fast neurons. There are 60 of them. Neuron 101 through neurons 160. These are the fast neurons. Neurons 1 through 100. Those are the input-output neurons. So there's 100 neurons here and 60 fast neurons here. Neurons 101 through 160. They're plotted down here. So each row here corresponds to 1 neuron. And the brightness, the black and white represents positive and negative signals, positive and negative values for those neurons. You'll notice that the fast neurons are also, the values of those fast neurons are also oscillating 3 times. And then when the robot is moving the block left and right, the fast neurons are again changing in values and oscillating 3 times again, but in a different pattern. So here you can see the brain of the robot, one part of the brain of the robot forcing up and down movement of the block, and then the same neurons, not a different neural module, causing a different oscillatory behavior left and right. Finally, we're going to look at the last 20 neurons, which are the slow neurons. You'll notice in this first half of the evaluation period, there is no obvious oscillation in the slow neurons. This is the conductor holding her baton. There's 60 of these neurons holding at a constant rate that is pushing the musicians into a particular song, which is the song of up and down 3 times. The conductor then changes her baton, and there's a little bit of oscillation you can see here, but she's doing something slowly, which changes the fast dynamics in the fast neurons, which causes the robot to move the block left and right. Same evolved CTRNN. We now give the robot a different set of goal signals that we feed into the network. We feed that goal signal into the slow units. We tell the conductor what song we want to hear. The conductor does her thing with the baton, and that pushes the musicians into yet a different song, which is move the block forward and back 3 times. Okay. In theory, we might be able to retrain this network to add a 4th behavior without disrupting the CTRNN's ability to emit the original 3 songs. We might be able to pack more and more behaviors into the same set of 180 neurons, unlike the simpler but non-scalable approach of neural modularity. There is a continuous debate raging in neuroscience about how modular the brain is. Do we store different things in different parts of the brain? Or do we store different patterns in the same set of neurons? It's much less intuitive for humans to understand that, but that's never been an impediment to Mother Nature. Hard to say it's hard to say at the moment how this actually works in the brain. The brain is so complicated that usually the answer is always all of the above, but it's sort of an interesting thing to think about. Okay, again, that was a little bit of some advanced material. If you didn't follow all of that, that's perfectly fine. Any questions about our block shaking robot before we jump back to lecture 9 and minimal cognition? All good? Okay. So just a reminder, we're going to now evolve very simple robots, but we're still evolving CTRNNs. We're evolving the taus, the weights, the gains, and the biases to produce in 4 different experiments, 4 different building blocks of intelligence. We looked at perceiving affordances. A robot evolves the ability to detect whether a pair of blocks is passable or not. We looked at another robot in which its hand can often occlude its vision. It's unable to see the block. Even if its vision is unoccluded, it's often not able to tell the difference between self and something else in its environment. We saw that we were actually able to evolve a robot that can do this. And we ended last time by looking at this robot, which evolves memory. It's looking through its 7 proximity sensors, but the moment it starts moving, it can no longer see the block. It can no longer see the circle. And as always, the robot has to evolve to minimize d sub I, the horizontal distance between itself and the circle when the black circle gets to the bottom of the screen. Okay. I don't remember whether we talked about this one or not last time. I don't think we got this far last time. Okay, so we take, as always, we take the best evolved CTRNN after evolution is done, put that CTRNN back in the evolved agent, and then perform a whole bunch of additional experiments to try and get a handle on how this evolved CTRNN works. We're going to take a whole bunch of black circles. Take a whole bunch of black circles. I'm sorry, I'm jumping around too much. We're going to take a black circle and drop it at the top of the screen 40 units to the left of the robot. So the robot is bottom center. We drop the circle top left. The trajectory shows the horizontal distance between the robot and the circle. I think we did actually talk about this last time. You'll notice that in the first few time steps of each of these trials, the trajectories are vertical, which means what? After a while, some of these trajectories become diagonal. What are the vertical parts of these trajectories tell you about what the robot is doing? If the line remains vertical, that means that after we have dropped the object from the top of the screen, the horizontal position is not changing as the object is falling. The vertical axis is the vertical position of the black circle. What does this vertical piece tell us? What is the robot doing? It's not doing anything, right? It's not moving. What does the diagonal lines tell us? At some point, the horizontal position does not remain constant, and the horizontal position starts to change as the object is falling. What does that tell you about the robot? What is the robot doing? The robot isn't moving the object. The object is falling of its own free accord. Alex says the robot is moving into position and then waiting. Okay, let's break this into two pieces. It seems the robot is moving into position because the horizontal, in all of these diagonal lines, you notice that all of these diagonal lines are converging on zero, meaning that the horizontal position between the robot and the object is decreasing. The object is falling straight down because the robot is not moving. And then suddenly the object is falling straight down, the robot is not moving, so the horizontal distance between them stays the same. That's the vertical part of the line. The diagonal part of the line, all of these diagonals are decreasing the horizontal position, or the difference in horizontal position between the robot and the object. The robot is now moving towards the object. Remember that I told you that when the robot starts moving, it can no longer see the object. Alex says the robot is moving and then waiting. Is the robot waiting? Does the robot move to where the circle is going to hit and then stop moving and wait for the object to hit the ground and catch the circle? It moves at as Lucas says, it moves at exactly the right speed to catch it. It gets there just in time, right? So all of these diagonal lines meet zero at a vertical position of zero. The robot, let's follow, for example, this trajectory here. At the beginning, the object is about 30 units to the right of the robot at the top of the screen. It falls for about 50 time steps, and the robot does nothing. Suddenly the robot starts moving, and it moves at a constant velocity. The object is falling straight down. The slope of this diagonal stays the same. The robot is moving, and bam, the robot gets there just in time to catch the object. The gray lines represent cases where the robot didn't quite do very well. You'll notice that all the gray lines don't actually end right at zero. The robot was a little bit off. It just missed the object. Okay, so we know something about how the robot behaves in this case. Why did the robot do poorly for these 4 cases out here, do you think? These 2 in the middle are a little harder to explain. Matt says the robot didn't move fast enough. Maybe the robot can actually move much faster than is represented by the picture here. It always moves at the same speed, and it looks like it maybe wasn't fast enough. But if you look at this line, the robot actually overcompensated. The robot actually went underneath it, and then the object hit on the left side of the robot. I think Missy is closer to the mark here. These are a little bit too far beyond its visual sensors. It got the right answer, so these objects must have touched the robot's proximity sensors, but just on the right-hand tip or the left-hand tip. So the robot had very little time to understand this object, to understand the angle at which the object was falling. Remember, we don't tell the robot that this object is falling straight down. The object sometimes can fall straight down or fall at an angle. It also doesn't know how fast this object is falling. So this is like me throwing a softball for you at you for you to catch, but you go blind about a millisecond after I let go of the ball. You don't have a lot of time to determine how the ball is approaching you and what you need to do in order to catch it. These ones in the middle, probably the robot did not do such a good job because these are probably far from conditions that the robot experienced during evolution. We've seen that before. Okay, here's another fun example. So in this case, they evolved they took an evolved successful C tier and N. These were evolved to catch diagonally falling objects. We're now again playing back the best evolved C tier and N, and you'll notice the robot does something different in this case. Let's look at this one over here. This object starts above and to the right of the robot, and the object starts falling even further to the right. The robot does nothing for, again, about 50 time steps, and then it starts moving, but it no longer moves at a constant rate in a constant direction. It's jinking back and forth, and again gets more or less underneath the object when it gets there. They took the same evolved C tier and N, played it back under a bunch of different conditions, which is now they're always going to drop the circle from top center of the screen, but that object is going to fall at different angles. And you'll notice the robot still does more or less the same kind of action, but that action is slightly different and starts happening at different times depending on the angle at which the object is falling. Okay, kind of interesting. Okay, let's look at the 4th and final experiment. This one's my favorite. This one is pretty tricky, and this is something that humans have a hard time with as well. This is known as selective attention. Right now, I am hoping that you are selecting or deciding to attend to this lecture. Some of you may be attending to your social media feeds while you're kind of listening to me in the background. We have more and more distracting devices in our lives these days. We have a lot of things that are pulling on our attention. We, although it doesn't often feel like it, we have the ability to select or focus on one of those external signals. Choosing or switching what to attend to at any given time is a difficult thing. When this lecture finishes, should you watch a lecture from another class? Should you do some homework? Should you catch up on what's happening on Twitter? Should you do some emails? Should you call a family member? There's lots of things you might choose to do or focus your attention on when class ends. What are the things that you take into account as you're deciding what to attend to next? Not an easy thing to do, and becomes increasingly difficult when there are more possible things that you could attend to. Okay, Our little robot, luckily, has only two things that it should be attending to. Two falling objects. As you can see in this picture, we're back to a robot that is moving left and right at the bottom of the screen. It has 7 proximity sensors. It does not go blind. It can sense and move at the same time. However, in this robot's environment, there are going to be 2 objects that are dropped, not necessarily at the top of the screen. They're going to be dropped anywhere within the screen, and each object is going to fall at its own angle, and it's going to fall at its own velocity. You'll notice this longer vector here represents the fact that this object is falling faster than this object. You can probably guess what we're going to evolve this robot to do, which is to catch both objects. A student who took this class several years ago, David Buckingham, decided to tackle this for his final project and came up with this. And I think this gives you a good sense of how this works. You'll notice as you're watching this video, there are several visual hints here about why this task is so difficult. What is it? First of all, the task is clearly to catch both objects when they reach the level of the robot. What is it that makes this task difficult? As Jimmy says, the difference in velocities. You'll notice that some objects start further away, but move faster. So the robot has to quote-unquote decide, it has to quote-unquote make a decision about which object to chase after. And the simple solution, which is always go for the one that's closest, is not always the best thing to do. So that's difficult. So selective attention is a relatively complex building block of intelligence because it contains its own building blocks of intelligence, like decision making. What else makes this task difficult? It's not just the relative velocities of the objects. Missy says sometimes it's impossible if the objects have similar velocities and starting times, but different end positions. Yeah, absolutely. So it can be difficult for the robot early on to know which object is going to arrive first and go after it. Alex says the second object exits the field of view of the agent. Exactly. So you'll notice as you watch this video, there are certain points of time in which the robot can see both objects and presumably compare their velocities. There's other times when it can only see one object and it has to remember. So memory is another building block of intelligence that's contained within selective attention. You probably can't remember everything you need to be doing today. Hopefully, some of you have a to-do list written down, and you know to come back to that list and remind yourself of the other things that are pending. The robot must have some neural version of a to-do list as well, because you'll notice when one of the objects passes out of its field of view, it remembers at least on which of its sides that object was on, and it goes looking for that object. Okay. So the fitness function is very much like what we've seen before. They're going to evaluate each CTR and NUM trials times. They have a fitness function where we have minus P here. So we know P is a penalty term because we're trying to minimize this amount over here. Anything to the right of a minus sign in a fitness function is usually a reminder that that's a penalty term. Anything with a plus sign in front of it is usually a reward term. We want to maximize that thing. What is P sub I? P sub I is the performance of the robot, and the performance is the sum of the distances between the robot when the first object hits the ground, D sub I 1. So what was the distance between the robot and object 1 when object 1 hit the ground during the ith trial? D sub I 2 is the horizontal distance between the robot and object 2 when object 2 hits the ground during the ith trial. So an ideal robot would get Ds of 0 for D1 and D2, and for all of the none trials. 200 minus a whole bunch of zeros is 200. The maximum fitness score the robot can achieve is 200. Okay, so as we just talked about, there are two separate problems or two separate challenges that the robot has to negotiate as it's evolving the ability to solve this task. The first problem is the passing objects problem, which is visualized here. This closer object is moving more slowly than the further object is. The further object is moving faster. How does the robot know? How does it determine, or how does it move in such a way that it gets the appropriate sensory signals to know which object is going to hit first and then know how to go after it? The second problem is the object permanence problem. The robot doesn't always see both objects. So chasing after one object often causes the other object to pass out of view. Okay. So we're going to end this lecture by looking at these 5 panels. These 5 panels are showing the behavior of the best evolved CTRNN. We're going to start with this panel here, where each of these 5 panels corresponds to 5 different environments, 5 different placements of the object pair, going from easy to very difficult. Okay, so not PO and not OP means in this particular environment there was no passing objects problem and there was no object permanence problem. Let's see what this looks like. We have time on the vertical axis like we've seen before, so you can think about moving from the top to the bottom of this panel as the objects moving towards the robot. What did the 2 straight lines represent in this panel? You'll notice both straight lines start at the top. One ends at this time and the other straight line ends at this time. What do these straight lines, what do you think these straight lines probably represent? The trajectories of the objects, exactly. So we have one object here that falls, doesn't say much about the velocity of this object. All we know is that this particular object hit the ground at this time, and this object hit the ground sometime later. What does the squiggly trajectory represent? Not much left, right? If the 2 straight trajectories represent the path of the object, the squiggly line must represent, as Logan says, the path of the robot. We'll talk about the 2 parallelograms in a moment. What can you tell me about the behavior of the robot in this environment? What did it do? Or what did it, maybe I should say, what did it seem to know? Or how did the robot do? So the robot, as Alex says, the robot caught both objects. So the robot was at object 1 when object 1 hit the ground, and the robot was at object 2 when object 2 hit the ground. As Logan says, the robot did well. It seems like it went for the closer one each time, right? So the robot is already zigzagging back and forth underneath the object that's going to hit the ground first very early on. So the robot seemed to know almost immediately which object to chase after. The moment it caught that object, it immediately went and was zigzagging back and forth under where the second object was going to hit. What do you think the two shaded parallelograms represent? Not the speed of the objects. A good guess. Any other ideas? As Logan mentions, it's the field of vision. So remember that the robot has these 7 proximity sensors. Obviously, as the objects start to move lower in the panel, there is a narrower field of view that the robot has. It's easier for the object to pass outside of the robot's field of view, which is represented by the parallelogram, this narrowing gap. So if the robot was here, for example, at this point in time, and the object had not fallen straight, but had fallen at a diagonal at this moment in time when the object trajectory moved outside the parallelogram. So jump back and forth here. The moment the object moved outside the parallelogram, the robot could no longer see it. It didn't happen in this case. The straight trajectory stayed within the robot's field of view. The fact that this straight line stays inside this parallelogram means that the robot was able to see object 1 throughout the entire time that object 1 descended the screen. The dark parallelogram represents the robot's field of view relative to the second object. All right? Okay. Took the same evolved CTRN, dropped another pair of objects, but now we introduced the passing objects problem. So the first object to hit, which is this object actually started further higher in the image. So it's this object up here. This object is higher, but because it's falling faster, it hits first. And then this object, we'll call it the dark gray object. The dark gray object started closer to the robot, but hit the ground later. What does the horizontal dashed line represent? The horizontal line, you can see that this line is drawn at a certain point in time. This horizontal dashed line is representing some event that occurs at this particular point in time. What is that event? What do you think happens that's important in this case? As Missy mentions and Sid mentions, when the further but faster object passes the nearer but slower object. What is the robot doing in this slightly more difficult case? It's clearly doing something different from what it did in this case. So remember, it's the same evolved CTRN, same robot. What's it doing differently now? It's catching the faster object first, so it does the right thing. The robot successfully catches both objects. But what is different? That's the same as in the first environment. What's different now? I don't know about you, but I spend a significant part of my time doing this every day. In the case of the robot, it's moving slowly back and forth under both objects, trying to decide what to do, right? What's the next best thing that I should be focusing on? What's the thing that's most requiring of my attention at the current time? And eventually, the robot figures out that it's this object that it should be attending to and gets there to catch it. Then very quickly goes back and catches the other object. You'll notice that both straight trajectories stay within both parallelograms. which tells us that the robot can always see both objects. There is no object permanence problem in this case. Let's look at the third case. Same evolve C tier and N, but now we're going to look at the converse case. No passing objects problem. Whichever object is closest, that's the one that's going to hit the ground first. But there is an object permanence problem. You'll notice this closer object hits the ground at this point in time. The robot, quote unquote, knows this because you can see it tracking underneath this object very tightly and successfully catches it. But at the moment that the robot catches this object, you'll notice that the squiggly trajectory is now outside the dark parallelogram. The robot cannot see the second object, the dark gray object, which is still falling. The robot clearly, however, quote unquote, knows where that object is. It knows that the dark gray object is on its left side and races to the left and gets underneath it in plenty of time to catch it. All right, let's go to the fourth case. In this case, we've got the passing object problem. The light gray object hits first, but it's initially further away. Here's the dashed horizontal line again, representing when this further but faster object passes this slower but nearer object. And you'll notice now, unlike in this case, the objects are actually falling in opposite directions from one another, forcing the robot. First of all, you can see, like we saw before, it's snaking back and forth under both of them, trying to quote unquote decide which one to go chase after first. It makes the correct choice, catches this one. It can no longer see the dark gray object. It's passed outside its field of view, but seems to know where it is. It takes it a little bit to sort of turn around and head in the right direction, and heads over there just in time to catch it. Okay, let's look at the fifth and final case. This is similar to the fourth case in that the closer object is moving more slowly. There's also the object permanence problem. The robot cannot see both objects at the same time because they're falling actually in parallel to one another, but they're far enough apart that the robot cannot see both of them at the same time. What is it that makes this situation more difficult than this situation? What's the difference between these two? The objects are falling parallel, that's true. That is one difference, but it's not the important difference. What is it that makes this really difficult? Missy says both objects are never seen at the same time. Notice that both parallelograms, they actually do overlap for a very short period of time, and then it is never possible for the robot to see both of them at the same time. In theory, the robot could move back and forth, look at one, remember, then go look at the other one, remember, come back to the first one. But it looks like the robot is not doing that. The robot seems to be looking at both objects for a very short period of time, and immediately after that very short period of time, it heads towards the initially further but slower object. So this gives us a pretty strong hint about how this robot works. It does not look, remember, go see, remember, and come back. It looks at both and compares and then does its thing. Okay. You might be able to imagine constructing a set of these environments. That would force the robot to evolve a neural network controller, where its only solution to solve this problem would be go, look, remember, come back, look, remember, go back, look, compare, and remember, and so on. Okay, That concludes our discussion on minimal cognition. Any questions on that before we tackle? We've got 11 minutes left. We'll tackle lecture 10 for a few minutes. All good? Okay. We looked at 4 different building blocks. We looked at 4 different building blocks of intelligence: perceiving affordances, distinguishing between self and non-self, being able to remember, and finally, selective attention. We're going to look at a 5th building block now. This one is, again, more complicated yet. This is a concept known as active categorical perception, or ACP for short. So let's talk about what active categorical perception is, and then we'll look at a robot that evolved the ability to do so. I'm going to start by asking you to think about this hypothetical task. Let's imagine that I sat you down at a desk, I blindfolded you, and I put one of these 11 objects, or I put each of these 11 objects in front of you, one after the other. I asked you to reach out with your hand, find the object, not close your hand around the object, leave your hand open, find the top of the object, put your hand on the top of the object, and push that object left and right. Seems like kind of an odd thing for me to ask you to do. Bear with me. As the investigators, we don't have the blindfolds on, we can see that these objects have a continuously changing curvature going from completely round to completely edged. There are no categories here. If I ask you to look at these 11 objects and tell me which are round and which are edged, hopefully you would realize that's not really it's an ill-posed question. You might say, well, these are mostly round, and then, okay, from here on, these are edged, but that's kind of an arbitrary distinction. Most of us would say there is no clear distinction between round and edged objects. But if we ask the blindfolded subject, who has blindly been asked to roll their hand along the top of these 11 objects, what answer would that subject give us? What's the answer? If we were to ask the subject to just describe what happened, tell us about these 11 objects, what might they tell us? If we had the time and resources, I would actually have you try this experiment. What do you think would happen? We have a blindfolded subject sitting at a desk. They might tell us they might give us the same answer as we would give, which is they're increasingly edged. They might resist telling us that there are categories here. Alex is getting closer. Some subjects might mention that some are easier to roll than others. What else might happen in this hypothetical experiment? The top row is rounder. Okay, maybe. If you really visualize this experiment, they might not be able to make a distinction between point 2 and point 3. Maybe there's a sticking point there. I want you to think now not so much about the blinded subject. We know what they're doing. They're pressing with a constant force downward with their hand and then moving their hand left and right. What's happening with the objects? What do you think might happen with each of these 11 objects? As Alex was mentioning, some might roll easier than others. Can we be a little bit more specific? Sid said the top row is rounder. Yeah, that's true. How might the object react to this action that the subject is performing? The top row actually rolls, whereas the bottom row stops on a side. So Alex is the first one in chat to mention there may be a clear distinction. On one side of the line, objects might actually roll, and on the other side of the line, the objects might stop on a side. I push, and one of these kind of boxed objects tilts on a side, and then it resists rolling any further. It starts sliding with my hand without rolling. Alex says it's the top row in which this is likely to happen, and not with the bottom row. So we've introduced a new idea already, that there's a category here somewhere. It's not round versus edged, it's rollable versus not rollable, under the specific action we've asked the subject to say. We've now re-entered the territory of affordances, right? It's not so much the geometry of the object that matters. What matters about an object is what we can or can't do with it. We are able to roll it when we do this action, or we just push it when we perform this action. But where does this distinction arise? Is it between the top and the bottom row? So for Alex, that would be between alpha 0.4 and alpha 0.5. Logan mentioned a distinction between 0.2 and 0.3. Where is the line? How would we know where the line is? It seems that there probably is a line somewhere. There are two categories here, rollable and not rollable. It's a bit of a trick question. You can't really determine where the line is because there's some additional information I haven't given you. What is that information? The speed. Okay, so what's the speed at which I'm moving my hand back and forth? That might matter. If I do this slowly, the line between rollable and not rollable may be at a certain point. Sid mentions the amount of force I apply. If I'm pushing down with a lot of force, then it's likely that more of the objects are going to become non-rollable. What about the surface of the desk? I haven't told you whether the surface of the desk is smooth or rugged. I haven't told you whether the surface of the object is smooth or rugged. All of these physical features of the object, the human, and the environment in which this task is being carried out determine where the distinction is going to be. But for our purposes, what's important for today is that there is a distinction. We've talked a lot about embodied cognition and how it might help an agent act intelligently in the world. One of the magical things about physically interacting with the world itself, in many senses, is continuous. There are certain objects, and those objects have a beginning, middle, and an end, so there is some distinction, but the world is also a very continuous place. More force, less force, more rough, more smooth, more squishable, more firm. There are little boundaries out in the world. A lot of boundaries or categories emerge when we interact with the world around us. And this little thought experiment that we just conducted is probably a good example of this. Agents, if they want to survive in the world, they need to sense categories, learn what those categories are, and then learn what to do for different categories. Is the situation I'm currently facing dangerous, or is this an opportunity? Is the thing that I see friend or foe? Is this piece of fruit that I'm holding, is it food or poison? All of these things are extremely important. Forming categories is very important. How do we form categories? Often looking passively at the world is not enough. The category is invisible. Often looking at a piece of fruit for an animal or a young animal is not sufficient to know whether it's food or poison. Maybe we take a very small nibble, or we smell the object, or we grasp the object to test its firmness. That might give us the information we need to know whether this is fruit or this is food or poison. For any given set of objects, we want to try and understand how those objects are compressed into one category, like rollable or not rollable. So active categorical perception is about learning the ability to perceive categories, but to do so in an active manner, to choose what to do to cause these categories to emerge. Often what we want to do is act in a way that reduces within category differences. These objects up here, they all have differences. They have different curvatures. But when we perform this action, those differences, those within categories collapse into the same thing. These objects are all rollable. These objects, which have different geometries, also collapse. We reduce the within category difference between these under certain conditions that they are non-rollable. We also are choosing actions to magnify between category differences. We want to act so that things roll and things really don't roll. We want to act in such a way that things don't partly roll. We want to make the boundary between categories broad. We want to really know, for this piece of fruit, not it's kind of food or kind of poison. Is it actually food or is it poison? We're out of time, so I'm going to stop here for today. You have a quiz due tonight. You're working on assignment 7. I wish you a good rest of your day. See you all back here on Thursday. Bye-bye, everyone.